Unit 1.5, Measurements, Chapter 3. This is the last chapter in Unit 1.5. It's a little bit longer. We go over some measurements on what we to do, and then at the end we look at doing some conversions and how we move from different types of units. Measurements consist of two parts, number and a unit. Otherwise, if a number is just a number. A lot of times in math you will calculate just the number. And sometimes in math though you will actually ask to convert to unit. Well, in chemistry we convert use numbers and units all the time, because what unit it is has an effect on what you actually measured. It's a way to communicate what did you measure. Did you measure mass or did you measure volume? Because if I said measure out 15, you're going to ask yourself 15 what? 15 grams, 15 milliliters. How do I do that? What in what I tell you, if I tell you grams, you'll know how to measure out grams. If I tell you milliliters, you'll know how to measure out milliliters. So you'll understand why that unit is so important. For mass is the amount of matter that something contains. It does not change with location, and that is opposed to where weight, how much you weigh, does actually change with the location, because the effect of gravity is mass. Weight essentially can be looked at as force is equal to mass times acceleration. So if you change the acceleration, i.e. gravity, you will change the force. And weight is essentially just a force, and that is not the same as a mass. It is important. You weigh less on the moon than you do on Earth. Your mass would be the same on both. So we want to make sure that those aren't confusing. There is a conversion. We very rarely actually convert in and out of grams and pounds, but it is down there at the bottom here for you. If you measure both the mass and weight of an object on Earth and on the moon, you would find that length, distance between 2 points. You drive, to Mankato, it's X number of miles. Well, we would probably worry about how many kilometers it were in science, but we're not going to be measuring miles, and we're not going to be measuring kilometers. We're going to be measuring things in more meters or centimeters or millimeters, and so our measurements are going to be different, and therefore we can use this a little bit easier. If you know you need a certain size or length of wood, or cut off a certain length of hair, it's important that you know how much that is. If you say, oh, I need just give me 2 inches off, and you cut off 4 because you can't measure, customer's not going to be happy. And so we want to make sure that we understand that the length is actually a distance between 2 points. A lot of times it's the length of a table, length of a piece of paper, length of a line, something like that. The volume is a little bit different, and that is the amount of space that the matter occupies, or matter is the amount of the mass that the matter has. Volume is the amount of that matter occupies, and we remember back to Unit 1 that gases take up a large volume. They have a very small mass, but they take up a large volume, and so we can play with that. And as we look and move forward, we will be measuring a lot of volumes. A lot of times, though, it will be volumes of the liquid, and therefore the volume of the liquid measurement will be anywhere between milliliters or liters. A lot of times that's how it is. And I see an error here, and it shouldn't be centimeters with a big 3 there. It should be centimeters cubed, or also known as cc's, centimeters cubed. And that's more of a medical thing. You'll probably, if you watch a medical show, you'll see, oh, I need so many cc's of certain drug stat, and it's cc actually just means cubic centimeter, which is a direct one-to-one. There's no conversion. If I say I have 5 cubic centimeters, that also means that I have 5 milliliters. It is a direct comparison, one-for-one comparison. So 5 cubic centimeters is 5 milliliters, and so on and so forth. For meters, it's a little bit different, and so we'll look at that as time goes on. But a lot of times, these end up being the most common measurements that we use for volume. Temperature, something we will also be measuring a lot of, and it's something that we can all have a understanding of, because you can go outside and you're like, oh wow, it's warm. Yes, that's because the temperature is blank. And so if you look at this, you can see that this is how it kind of works, is that you have a temperature. Now we have different scales, and we have the Fahrenheit scale, which we use in the United States. We have the Celsius or centigrade scale that is used more internationally. But in science, we actually have one that's known as the Kelvin scale. Notice it doesn't have the degree sign, and that's because it's not actually a degree of anything. It's actually a scale. And so it's usually used to use what is known as the absolute zero, but it's really good in using for gases, which we will use at the very end of the year here out in chapter, or unit 9, I believe, 8 or 9. So how do we convert between the two units? Well, this is also on the back of your periodic table that you were given in class, and these are a little bit more of a kind of a absolute way of doing it. But a lot of times what we tell students is an easier way to do this is if you wanted to convert between Celsius and Fahrenheit, and say you were watching the Olympics and they were talking about how it was 25 degrees Celsius, and you're like, wow, that's really cold. But it's really not that cold. If you double 25, you would get 50. And then if you add 32, you would actually get 82 degrees Fahrenheit. It's pretty darn close, because you can see the conversion is actually 9/5, which is very close to 2. It's like 1.8 something, I believe. And so it's the same thing converting backwards, is that if you saw, like, what, 82 Fahrenheit, I wonder what that is in Celsius. Well, if you subtract 32 from that, you would get 50. And then if you divide it by 2, you would get 25. And so it works. It's not going to be an absolute, but it's going to get you very close. And sometimes when you're, say, in Canada or in Mexico or another foreign country that uses Celsius, you can kind of get the conversion very easily in math that you can do in your head. A temperature of 30 degrees Celsius is equivalent to what in Kelvin? Energy, the ability to produce heat or do work. You need energy to do work. You need energy to walk. You need energy to talk. You need energy to stay awake in your desk. You need energy to do everything you need in your life. A certain amount of energy. The most common unit is a calorie. It is important that we make note that that is a lowercase c in that calorie. So it's not the same calories that you eat. So we'll get into that in just a little bit, though. The SI unit is that we use is the joule, that we give respect to James Joule, he's a brewmaster in the, I believe it was France. And so we'll talk about him when we talk more about the energy, though. There is a conversion between 1 calorie is equal to 4.18 joules. But when you think about food, you actually, and if you look on the back of your pop or back of a bag of Doritos, you'll actually see that it's a capital C calorie, and that's equivalent to 1,000 calories, or most dietitians prefer the use of kilocalorie, and that uses the prefixes that indicate how much bigger that base unit is. And so a kilocalorie is equivalent to a capital C calorie, and so it can be kind of confusing. That's why we just usually use the joule. Makes it less confusing. Which of the following is not a base SI unit? Density. Now, the density is not one of our basic units of measurement. It is actually a one that requires two measurements. It requires mass and volume. So density is the amount of mass in a given volume. You'll see in your iBook that we talk about will it float, and that's kind of the more dense something is, the more mass it contains in a given volume. And so be careful when you look at the videos on will it float, and it kind of goes through and you kind of think, well, maybe this won't float, but it might because of some of the little subtleties. So that density is something that can usually generally decrease as the temperature increases. So it would be as temperature goes up, density goes down. And so it is important that we pay attention to that. And so they are kind of inversely proportional, as you would look at it. Some densities that we see of some of the common items that you might find is density of gold. It's extremely dense. It is more dense than lead, and some people find that very interesting because lead is very, very dense. So is mercury. Aluminum is not as dense, and the table sugar, why does it sink to the bottom? Well, it's more dense than water. So if it's more dense than water, it sinks. If it's less dense than water, it floats. And so if you look at where water is here, we'll see that, oh look, ice is less dense. And that's an oddity for water, actually, and most of the time solids of their compared to their liquid form are more dense. Unfortunately, and actually very fortunate for our fish friends, that ice stays at the top, because otherwise the ice on the rivers and in the lakes would actually freeze from the bottom up, meaning the fish would most likely die, and that wouldn't be good. Now, ethanol is an oddity in that it actually mixes with water, and so you have to be very careful about sometimes how that happens. When we look at these chlorine and argon, and you look at these and say, wow, these are really dense, again, we must pay attention to the units that are being used. The liter is 1,000 times bigger, so we're dealing with a much larger volume. And so to keep the numbers more understandable, we change the unit so it's easier for us to understand what we do with that. We can actually calculate density, and that is the density is the ratio of materials mass to its volume. And so we have a very nice rudimentary, very algebraic equation that mass is equal density is equal to mass divided by volume. Now, one that sometimes people will find a little bit maybe easier, and that is that it will be here's we can add a piece to this, and let's see if I can get this to work here. Okay, kind of do. And what this looks like here is that this circle equation, I think Mrs. Otto does a triangle equation. And so if I wanted to find out what's the equation for density, I just cover up the D, and I see that M divided by V. If I wanted to solve for V, I cover up the V, and now I have the equation of mass divided by density. If I wanted to find the mass, I cover up the mass, and I can see that it is density times volume. So it takes a lot of the thinking algebraic manipulation out of it. And so I really do enjoy or like students using these circle equations, triangle equations, whatever it is. They work. So let's try one out. Let's try an equation out. And so we say a cube of ice has a mass of 6.2 grams and a volume of 6.75 cubic centimeters. What is the density of the ice cube? And you're like, well, I can just look it up. Well, maybe this is a different type of ice, and maybe this was frozen in a different way. And so we have to go through this process and saying, okay, what do I know? What are the things that I know? I know mass is equal to 6.2 grams. I know the volume is 6.75 centimeters cubed, which again is the same as a milliliter, but it's easier probably to measure something solid in cubic centimeters. What do I not know? I don't know the density. That's why it says, what is the density? So I don't know what the density is, so that's my unknown. Well, what equation do I use? Well, I just talked about the equation, and so mass divided by volume is equal to density, so that's the equation I use. I'll just put in what I know into my equation here. And so I can go 6.2 grams divided by 6.75 cubic centimeters is equal to my density. Now, how do I calculate that? Well, that's where a calculator comes handy. And it doesn't need to be a crazy elaborate one, but one that works usually is best. And so now we can see that the density is equal to 0.9, and I'll say 2 grams, because it wouldn't be a number, it would just be a number. It's grams per centimeters cubed. So it is a number and the unit. Now, we have another problem. You don't know what it is. It's a glob of green goo. And so we have this given to you and say, here, find out what the density is. Because that might help us figure out what it actually is, or maybe what it's made of. And so we have, again, this idea. What do I know? I know it has a mass of 5 grams. I know the volume of that green goo is 2.5 milliliters. Why milliliters versus centimeters cubed? Maybe it was easier to pour the goo into a cylinder. I don't know. The density, don't know what that is. And again, so what can I find? How do I find density? Well, there's only one equation that we've talked about to this point, and that is density is equal to mass divided by volume. And so we go through this process and we see that 5 grams divided by 2.5 milliliters is equal to density. Well, I'm hoping you know what this answer will be, but if you don't, plug it in your calculator. So 5 divided by 2.5, and you'll see that the density of this is 2 grams per, almost put cubic milliliter, sorry about that. Even got more in there. Erase, and I'll just go, that didn't work either. And so we have centimeters cubed, or 2 grams, and actually both would be acceptable on a test, either one. So here we go, and I just went with it. So there's my density of my green goo. Now we can look it up on a table and see what kind of looks green and globby or whatever, and see what is 2 grams per milliliter, 2 centimeters cubed. If 50 milliliters of corn syrup have a mass of 68.7 grams, the density of corn syrup is what is the volume of a pure gold coin that has a mass of 38.6 grams. The density of gold is 19.3 grams per cubic centimeter. As the temperature increases, the density of most substances So now we looked at how to make some measurements doing some density. Now let's look at what's called dimension analysis, or also known as converting. And so we have that conversion factor that will be necessary. That's our per expression. It's usually written as a fraction. And so we kind of go through this process of the systematic way. There are a number of different ways to do converting. If you find the way that you do converting in math is more your style or is easier to understand, feel free to use that. You do not have to do it the way I do it in chemistry. If the math teacher does it a better way, excellent. Hey, teach me how to do it. Maybe it's a way that will make your life as a student easier. That conversion factor is a per expression that usually that we will write as a fraction. There are some things that are commonly known is that there is 2.54 centimeters in 1 inch. If you go to a ruler and look at that, it's there. There is 1,000 milliliters in 1 liter. And these translate into a ratio. 1 inch is per 2.5 centimeters, 2.54 centimeters into 1 inch. And that these are some per expressions that we use. So a way to kind of visualize that is if I had a meter stick, it was this long, it has 100 centimeters. And actually, if you look at it, it actually counts out to 100, which is really nice. But now if you look inside that 10, well, then there's 10 centimeters inside that 10, there's stuff inside there. And if you look really, really tiny, then there's 10 millimeters inside 1 centimeter, and so you can get some really good conversions just by looking at a meter stick. And so if you do this from a conceptual point, is that you'll see that the larger unit gets a large number gets a small unit. A large unit gets a small number. I usually will look at it kind of and ask the question to myself of what's bigger, a meter or a centimeter? And because if you're bigger, faster, stronger, usually you're number 1. And so you get the indication of the 1. Now, how many centimeters are in a meter? There's 100. And so that's kind of a way that I also reason it through myself as we go through. But this is another illustration to kind of help you visualize it. So the directions for an experiment call for each student to measure 1.84 grams of copper wire. I have a spool of copper wire with a mass of 50 grams. How many of you can do the experiment? Am I going to have enough? And so we have, again, looking at what I know that I need 1.8 grams of copper. I have 50 grams of copper. Well, how many people? And that's the thing, is that we go per student on that, and then we can go, oh, that's how I get that. Because if I take and put 50 grams on top and go, I have 1.84 grams, and also write this as a fraction, and that's where a lot of people aren't always the best at. We can see that actually our grams will cancel out algebraically, leaving us with just students. But now if we use our understanding of math and converting with, or multiplication and division with fractions, we'll actually see that the students actually goes from a denominator's denominator to the numerator spot. So but the number that I get is 50, because that's actually easy to do, divided by 1.84. And I see that, oh, I can have 27.2 0.2 students. I don't think I've ever seen a 0.2 of a student. Sometimes they're not always mentally 100% there, so maybe that's what it is. Maybe only 0.2 students can do that. I comfortably would say that about 25 to 27 students can do this, based on the fact that some people don't measure good, and therefore we're going to have some people that use more than they should. So let's convert the following, and so we'll kind of set these up a little bit differently, and so we'll kind of go through that. We'll start off with the what I have, and so I have 750 centigrams. Well, if I want to get rid of centigrams, I need to put the centigram on the bottom. If I want grams, I put the grams on top. And I say, which one's bigger, gram or a centigram? Well, a gram is bigger. How much bigger? Well, that's what we ask ourselves. How many centigrams are there in a gram? Well, the number actually helps us out in that it actually is century 100. So I divide by 100. And algebraically I can see that my centigrams cancel out. And so I can divide by 100, or I can do this crazy thing in moving our decimal place over 2 places to get 7.5 grams. Now in the next problem, I see that I have 7.38 grams, and so we'll start with 7.38 grams. Well, I need to move that into kilograms. Let's go kilograms there. And that means I need to get rid of grams. Well, which one's bigger, a kilo or a gram? And this is why in the earlier chapter we looked at that conversion chart as which one is it? Is a gram the base unit? It is, and therefore what's above it? Well, a kilogram is above that one, and so if it's above it, it's bigger. Therefore it gets a 1. How much bigger? Well, that's where that conversion factor comes in, and that it's 1,000. A lot of times you will see that 1,000 is a very, very common conversion factor that we use. Now this would be dividing by 1,000, and therefore we'd move the decimal place to the left 3 times. But because we have a good understanding of scientific notation, hint, hint, that you should or could go 7.38 times 10 to the negative third kilograms. Because if you put in your calculator, it might give you a whole bunch of zeros, and those zeros are going to be like, that's confusing, I don't like it. So that's what we go with. Something that could very well potentially happen is 15 milliliters into liters. And so we start with 15 milliliters, and capitalization on the L does matter, believe it or not. And then I say, well, I want liters, and then I want to get rid of milliliters. Which one's bigger? Well, that is the liter is bigger than the milli. Milli is 1,000. A lot of people forget that, and they think, oh, that means it's, yes, it is not that. It's not, milli is not a million. That's micro. That's why we use that. And so here we have that converted out, and it's going to be really small, and that would make sense. 15 milliliters is not a lot. If you put 1 liter, you put it in a 1 liter thing, you're measuring a very small amount. And so you're going to get a very, very, very small number. And we can use scientific notation to work with this. And we can move the decimal place 3 places over, or we can use scientific notation to say that I have 1.5 times 10 to the negative second liters. Now the next one has us looking at something a little bit different, which means it's a 2-step conversion. And so we have milligrams to grams to kilograms. And so what we're going to go with, or what we're going to do, is we're going to start with our 15 milligrams. Get that G in there, and we convert that into grams first as we kind of follow this step-by-step part. And so we can see if I do that, a little thing here, I'll get milligrams, and I want to convert into grams, and I can go, okay, which one's bigger? Well, a gram's bigger. How much bigger? Well, 1,000 times bigger. And my units cancel out. Now we have a very interesting question: is what do you do? Do you put that into your calculator and hit 0 or enter? I'm sorry, and then go through the next conversion process, or do you tack on the next conversion, and that is from grams into kilograms? And so what you do is dependent upon you. You have to do what you feel comfortable with. Either way, it's going to get you the same answer. The number is going to be maybe a little bit more daunting. How do you put it into your calculator? Do you put it in? And so sometimes it might be better to go a little bit more of a step-by-step, because I think it's important that we get ourselves used to doing these multi-step type things, because we're going to be using it a little bit later. We'll do that. And so I have 15, and I can move the decimal place over 3 times, and then again move the decimal place over 3 times, and I see that I get a very, very small number, and I'm like, well, that doesn't make sense. So why don't I use scientific notation? And so I do. I use my scientific notation to help me out a little bit on this part, and I move my decimal place over 1, 2, 3, 4, 5, and I see that it's actually 1.5 times 10 to the negative fifth. One little point there is not looking good. And so we have that conversion factor. There are more examples in Schoology and in your notes. 1 megagram is equal to 1,000 kilograms. Which of the following would be correct conversion factor for this relationship? The conversion factor used to convert meters to feet changes. How many micrograms are in 0.0134 grams? Express the density of 5.6 cubic centimeters in kilograms per cubic meter. That's the end of Unit 1.5, or what used to be Unit 1, Matter and Measurement. It used to be all one big unit, so it's pretty much the end of Unit 1, which is pretty darn close to where we're at.